Hey guys, well, welcome back to another notes video. Mrs. Gustodo did an awesome job over there in Target 1C describing to you how to find the slope of a situation where you know two ordered pairs using the formula. And what we're going to finish the notes with today is some application of rate of change, specifically a constant rate of change. I think one thing that we would all love to do, if you could think of a superpower that you would love to have, being able to know what's going to happen or accurately predict the future would definitely be pretty high up there. And what we're going to talk about today, guys, is actually just doing that, is using math, using a constant rate of change to actually try and predict the future. Now, it's not a superpower. This isn't something we're going to do perfectly or maybe ever even at all accurately, but it's about making the best possible guesses at what's going to happen in the future based on what happened in the past. I actually just watched Cars again with my daughters the other day, and Maynard. If you've not watched Cars, Maynard is the old rusty pickup truck, was telling the Lightning McQueen, the main character, about how he drives backwards, and it's he said he figures out where he's going by looking at where he's been, right? And so that's really what we're going to do, is we're going to look at something that has already happened, use that to kind of gain some information, and then use that information to project forward into what might happen in other situations in the future. All right, so let's dive right into this situation here. So we've got Jordan, Jennifer, and Allison are going on a road trip to Cawker City, Kansas to see the world's largest ball of twine. And yes, I did my research on Google. That is the world's largest ball of twine, and that is a real place. So it took them 11 and a half hours to travel the 730 miles from Grays Lake to Cawker City. All right, so the first question is gathering the information. So how do we take what we already know and write it in a way so that it's useful mathematically here? Oops, sorry. And the key is, what is the miles per hour? Okay, that's a rate of change, guys. That's a slope. Instead of rise per run, we're now looking at an application of real life here, miles per hour. Now, the other thing to notice here specifically is that the hour is singular. Singular. All right, we're going to go with that. That might not be spelled right, but I'm doing the best I can here. All right, singular. And so that's going to play an important part of how we get to a final answer here. But what we see is miles per hour. So essentially what that's saying is the same way rise per run is rise over run, we are essentially saying miles over hours. Well, if we look at what we have up here in the problem, we have a number of hours and we have a number of miles. So we can pretty easily just take the miles and put it over the 730 over 11.5. But here's where the singular piece comes in, because right now, this is not miles per hour. This is miles per hours. And we don't want that. We want that to be singular. So the question becomes then, how do we get 11.5 to not be 11.5, but be singular, be 1 hour? Well, the way you change any number into 1 is just to divide it by itself. So if I divide 11.5 by 11.5, that will then become 1 hour. Well, we remember our rule in a fraction. Whatever we do to one part of the fraction, we have to do to the other. So I'm essentially dividing both the top and the bottom by 11.5. So just take your calculator and do 730, as I'm doing here, divided by 11.5. And rounding is, guys, a lot of times this is going to be a little bit messy. You're going to get decimals. You're going to get some numbers that don't work out nice and neat, and that's okay. Let's round to 2 decimal places, and what we would find is that we would get 63.48 miles. Let me see if I can write that better there. Miles per 1 hour. All right. That is the rate of change, the miles per hour that these 3 young ladies had during their trip. And so this is the past. This is what has already happened. It is a fact. It is known. Now what we're going to do is, and here's the big key here, assuming the rate of change stays the same. Now, do we really think that anything in life is going to stay exactly the same as it has in the past? No. We know there's going to be some differences and some changes. But the key is, can I take what has already happened, what we know is fact, and try and make an educated guess, a plausible prediction about what would happen in a different situation or a situation down the road in the future. So let's look at the second question here. The second question says, assuming the rate of change stays the same, meaning assuming that 63.48 over 1 remains the same, how much further could they travel if they drove 3 more hours? So what we're saying is, if this stays the same, now stays the same means equal, right? So if what we had in the past stays the same, right? Let me write that in here, right? This equal part here is the stays the same. That's where we get that equal sign from. And what does it stay in the same to? Well, how much further if they drove 3 more hours? And now this is key here. How much further, right? That's what we're being asked. We don't know how much further, so that's our variable. And when we're saying how much further, that is about miles, right? So we're being asked in this question for a number of miles. And when we're setting this up, we have set up miles over hour in the past, so we have to have miles over hour in the future here. So the unknown, what we're being asked for here, has to be x in the numerator. And what we are told is for time, that it's 3 more hours, right? So essentially what we've done is we've set up an equation here where we have a fraction equal to fraction. And this type of equation, guys, is a special name. It's probably something you've worked on in the past in some of your pre-algebra classes, 6th, 7th, or 8th grade, and it is called a proportion. I'm going to come off the notes a little bit here, up above, and just talk about a proportion really quickly. A proportion is going to be any equation where you have a fraction, I'm just going to say 3/4, equal to another fraction. Let's just say 6/8. The key is that it's actually going to be equal. Is 3/4 equal to 6/8? Yes. How do we know that? How can I prove that they're equal to each other? Well, one way we can prove they're equal to each other is by a mathematical principle called cross multiplication. Now, I want to be very clear on this. This is the only time in all of math that you should be cross-multiplying. Never should you cross-multiply when you're multiplying fractions. Only when we're working with a proportion and we're trying to either verify or solve a proportion. So what we see is 6 times 4 is 24, and 3 times 8 is 24, and those two things are equal. So this proportion checks out because the cross products are equal. So we can use this same principle down here about a proportion, or that up here, this principle up here about proportions, we can use that down here to solve this equation. All right, because here's the deal. If these two fractions are equal, which we're saying they are, then this multiplication, cross multiplication, and this cross multiplication should be equal. So 3 times 63.48 should be equal to 1 times x. Well, 1 times x is pretty easy. That's you're not going to get pretty much any easier arithmetic problems than that. And using our calculators, all right, we will get 90.44 equals x. Now, what was it? Again, what is x? X is how much further could they have driven. So our answer is 190.44 miles. That is the answer to the question. Now, again, is that going to be precisely the exact number of miles they could drive in 3 hours? Probably not. Is it a very educated, plausible estimation that we could use in real life? Yeah, I think it would be. All right, let's look at one more together here in this example. Assuming the rate of change stays the same, all right, how long would it take the girls to travel only 500 miles? So again, stays the same. So we're going to have that 63.48 miles for 1 hour stays the same equals, but now they're changing things up on us a little bit. Notice now they're asking how long would it take? So now they're setting the variable as time instead of distance. So the x has to go in the denominator, and we're given our numerator here is 500. All right, guys, we're going to solve this exactly the same way. This is a proportion. Two fractions equal each other. So if this is actually equal, which we're saying it is, then 500 times 1 should be equal to 63.48 times x. So we get 63.48 times x equals 1 times 500, which is 500. Now notice the difference between these two equations here is x was isolated right off the bat here, and here we've got to do a little work to get it alone. So we're going to take the 500, we're going to divide it by 63.48, because we're dividing by 63.48, sorry, on both sides to cancel that. So I divide by 63.48 on this side, and we will get x equals 7.88. Well, again, what we were finding? We were finding hours. So if these three girls wanted to, road trip another 500 miles, or let's just say they were going to, on the return trip, only drive first 500 and then take a break, they should estimate that it's going to take them just under 8 hours to travel those 500 miles, and they should plan their trip appropriately. All right, so this is an example of how we can take a real-life rate of change, a real-life slope, if you will. Rate of change is just slope in, in a coordinate plane, right? And use that to then make estimated predictions, educated predictions about what's going to happen in the future. Want to look at one more example together here, just so we can talk about this graph here, and that's 3A. So Coach Dahl took his freshman volleyball team out to eat at Buffalo Wild Wings after a big win over Grayslake North High School. He had 18 people on the freshman team, and the total bill was $180. What was the cost per person for the meal? So we're talking about money per person. And again, notice person is singular. So when we look at what we have, the amount of money is 180 and the number of people is 18. But we got a problem because that's not singular. So what do we have to do? We have to take the 18 in the denominator and make it singular, divide by 18 in the numerator. And what we're going to get here for our final answer is $10 per one person. All right, so that's our rate of change in the past. Now, B and C, you can do those. I'm going to let you work on those on your own and check the notes on real-time board to get answers to those. We're not going to show you all the work and the answers. They will be, all of these notes, guys, in these pages, all of number 2 and these 3B and 3C, I will fill in all the work on the notes in real-time board, but 1, for time's sake, and 2, because I want you to actually have to go and use the notes. I want to make it there. But what I want to talk about is how do we then turn that into a graph? We talked about how to turn that into an equation when we're making predictions in the future, but how do we take this $10 per one person and turn it into a graph? Well, we can take a coordinate plane, right? And we can label our X and Y axis. Now remember, rise over run is Y over X. So when we think about this rate of change, if we're thinking about turning this into a graph, right? If we're going to turn this into a graph, we have to understand that rate of change in slope is Y over X. So rate of change in real life on a graph is still going to be Y over X. So what that's telling me is that dollars is going to go on my Y axis, right? And the number of people is going to go on the X axis. Right? And you can see I've already labeled that down here in the notes, but you're probably going to have to label this on your own in the homework, and if this was on a test or a quiz. So you can see the number of players is already labeled on the X axis, the number of dollars on the Y axis. Guys, the intervals that I used here, it's a little bit up to you to decide that. You need enough space that you don't kill yourself trying to put 100 million little tick marks on the graph, but you also want to make sure that it's not too big that you have trouble being accurate. If your intervals get too big, sometimes it's hard to know exactly where to put the points. But we have $10 per person. So if there are 0 people that go, we have $0 spent. One person, $1. So I'm going to represent that in two. So two people, $20. Three people would be $30 here. Four people would be $40. And all I'm doing is doing a rise and a run. I'm going up 10 and right one, up 10 and right one. Five people would be $50. Six people would be $60. All right. And hopefully what you see is, and applying and graphing this rate of change, what we're actually graphing are points that would form a line. So after so many points, we could kind of stop worrying about the points and just kind of draw a line to estimate. So here's 60, right? Now it's not going to be perfect, right? 60 and what 16 should be points on that line as well. But this is what we're looking at here in terms of making sure not only can we use a real life rate of change to make predictions about the future, but also we want to be able to make sure we can graph it and represent it visually on a coordinate plane. Well, that takes us to the end of the notes, guys. If you got any questions, right, please ask, email, Schoology, ask questions through ClassKick. Mrs. Custodio has some office hours on Zoom. I will during the second week have some office hours on Zoom as well that you could log in and ask us in person about things. But guys, it's just really important that you're engaging, that you're giving it your best effort, and we do not expect perfection at all. If you're confused, that is okay. It is okay to not be okay with what you're learning. The key is it's not okay to stay there. It's not okay to stay that way. So please make sure we're engaging, we're trying, we're struggling, we're developing questions, we're asking questions, we're getting answers, and really coming out of this whole process, really understanding what we're dealing with. All right. Well, until the next video, this is Mr. Dahl signing off saying, have a great night, Grayslake Algebra Recovery class.